Good afternoon. My name is Rosendo, and this is team number one's challenge.
Collaborative robotic solutions require precise and reliable control system to perform tasks efficiently in real-world environments. In this project, the main objective is to develop a motor control system using ROS2, and the challenge lies in achieving stable high-performance motor behavior that can quickly adapt to varying inputs and conditions while respecting hardware and software constraints. Among the potential solutions, we adopt a PID controller to regulate the motor speed and behavior. This controller operates with the ROS2 environment, ensuring continuous feedback and adjustments even under dynamic loads. Crucial to this approach is the integration of multiple ROS nodes, each handling distinct tasks such as sensing, computational, and actuation.
So we had our Gantt diagram. We divided into 5 weeks, which was robotic introduction, ROS practicalities, micro cross communication, open loop control, and our final challenge to present in this part. We also have the software developments, the hardware integration, and our analysis and optimization, which was evaluation of system and performance parameter just to adjust our PID into the controller.
So for our project architecture, we basically have our main nodes. The first one is the setpoint node, that is the node implemented on Python. The second one is the motor controller node, which is implemented on the ESP32. So basically, the setpoint node on the Python sends topics for the PID gains and also for the setpoint. Then the motor controller node sends the value of the motor output. So for basic libraries that we use MicroROS and RCL and standard messages for the Arduino code, and RCLPy and NumPy for the Python node.
The way the system works, it's basically that we start the MicroROS agent to initialize the connection with the microcontroller. We launch the ROS2 node to generate the set points with the different type of signals. Then in the ESP32, it's initialized the motor and encoder pins with touch interrupt to encoder for position tracking to calculate the angular speed. We set up the PWM for motor control, and then it initializes the MicroROS2 node. And it creates subscriptions for the set points and the publishers, and then it initializes the executor to handle all the ROS2 callbacks. In the main loop, it reads the encoder positions and calculate the angular speed according to the values it reads. Then it publishes the encoder position and it speeds in a topic. And then it compute the errors that we program to be as desired speed minus measured speed. Then it applies the PID control to compute the PWM output, and it updates the motor speed using compute the PWM value. Then it processes the MicroROS executor to handle all the new messages, and it repeats the cycle.
For ROS implementation, we've basically created a launch file in Python so we can simultaneously launch the setpoint generation node and also the RQT-plot to visualize the setpoint and the motor output. We've also used messages. As said before, we used the float32 for the PID parameters. And then we've also created a parameter file so we can declare the values for the wave, and it's a string, so we have to put or sin or square or step, and also for the PID, the float32 values. Also, we use namespaces so we can create two groups on the launch file. This so if we can use two motors at the same time.
For sampling time selection, we just like motor dynamics control, which we use that equation. And for last, we got our final choice, which was 0.02 seconds, which equals to 50 hertz. And you can see how we translate it to hertz. And this means that if we use this sampling time, it's easier for us because it's optimal precision and stability. If we increase it, it could be maybe overload in the ESP32, and if we do it less, it can be a slow response with a high error.
For parameter adjustment methodology, we use a heuristic trial and error approach. We started with P equals 1, I equals 0, and D equals 0. First, we increase the P to make the output follow the set point while minimizing oscillations. Then we adjust I to eliminate steady state error and speed up convergence. We didn't use D since it wasn't necessary for stable control. And so P and D were not to get the desired response, and these were the results.
Advantages and disadvantages of the controller. The advantage is precision in controller, modularity in ROS, and flexibility for different models. Disadvantages, possibility communication delays, and hardware limitations. Challenge and reflections. The difference between the simulation and experiments is the simulation showed ideal results without noise, while the physical experiment presents variabilities and with the noise, communication delays, and limitation on the real hardware, causing a slight difference in the dynamic response of the system. As team, we successfully developed and demonstrate a closed-loop motor control system that combines MicroROS and ESP32 with a Python ROS2 node for generating dynamic set points and tuning the PAT parameters by balancing lower-level real-time tasks like encoder reading, PWM generations with higher-level node communication functionalities ROS. In the process, we learned to mitigate hardware noises, fine-tunes parameters through iterative testings, and overcome communications. Thanks.